You just work on assignments. Okay? Let's get into this tutorial really quick. It's a pattern of the code, and you have to follow the pattern in the future. It's a very similar pattern for all these following tutorials, as long as the timers are getting involved. So here's the pattern. Okay, so first you give a starting counts to the counting register 1. That's in the setup function. I mean, if you don't do this over here, it's probably still fine. Let's take a look. So you just put that initial value there, but you don't start the timer, okay? Once it gets into the loop, see what's going on. So I press it. Remember the example, what this does? You press it, it beeps once, right? So actually the duration that you keep your finger on the top of the button defines the duration of the music note. It's not a normal song, remember? What's happening here? If you want to play a song with the correct durations, you have to control your finger really accurately.
If you load
otherwise,
the example code from the web.
See, I use my finger to control the durations, right? So I have to do this. So that means if I don't press it, there won't be any song. So to implement it, you can see here. Firstly I give a count. So this is the number of counts, which defines the frequency of the song of the note. And once it gets into the loop, so that's a pattern you need to follow in the future. Okay. See, the first one is using the microsecond delay. Let's just skip that one for now. Let's directly get into the second one, which is the bottom button. So if it is low, which means it's a price is detected, and while this is still low, which means it's still being pressed. Okay, still being pressed. Just double check on that. Okay. So I don't have a semicolon to just stop here. So which means this while loop has something in it. All right, so take a look at this one. This could be confusing. Other microcontrollers don't really assign logic levels to the bits in this way. It only happens to Arduinos, and all these, I think it's AVR. It used to be AVR type of microcontrollers from Atmel, right? Atmel was a company making microcontrollers who designed Arduino and Mega, all these microcontroller series, and was required by Microchip a few years ago. Microchip has branches in Texas, in Colorado Springs, and so it's a good employer. Okay, and so other microcontrollers in Microchip, they don't assign bits, logic levels to the bits in this way. But this is how Arduino does it. How this works? This is confusing. Why you are shifting a bit? Remember CS10, so it's CS1 is a timer, 0 is a bit, right? That's the prescaler, one of the prescaler bits. So I'm shifting 1, which is just a 1 byte, even though it's a number, it's a decimal number, but however you can imagine all the decimal numbers are being stored in the CPU or the microcontroller by a byte, right? So 1 is actually 7 zeros and 1. It's a byte, keep in mind, it's a byte. Okay, so it's just a number 1, it's the decimal number 1, but 8 bits, right? And this is being shifted to the left by CS10. That doesn't make sense. Like I'm moving 1 to the left by something. So keep in mind that in Arduino C code, this one, because this bit is the timer 1's prescaler controller's bit number 0, right? So this is a 0 bit. It's an LSB. So it represents number 0. You can understand that way, just let you guys know. This CS10 here, right here, can represent number 0. So basically what you are doing is you are shifting this byte, which is 7 zeros and 1 single 1, right, to the left by how many bits? 0 bits. 0 bits. So we're not shifting anything. Interesting, right? I mean, as long as we understand what's going on, we just keep using this because this is all these standard, Arduino controlling microcontrollers are programming in this way. So let's follow because there must be some reason for that. The compilers really likes this way, but you definitely can do it in other ways. But there might be mistakes. But let's just keep in mind if we want to set a single bit in here to 1. We are doing this. Let me show how this works on the paper really quick. So the purpose of this line is to set the CS10 to be 1. But how do we do that over here in Arduino's programming environment? Remember the bar here is OR logic, right? So this is basically this guy, so the TCCR1B. This whole thing is the 8-bit. So this guy do a bitwise OR with this guy, which is 0, 0, 7 zeros and 1. Okay? And shift it to the left by 0 bits and do a bitwise OR logic. And then assign it back, the result assign it back to TCCR1B. That's what's happening here. This is 8-bit 1, right? And CS10 represents number 0. And you shift 1 to the left by 0 bits, which is not shifting anything. Okay? And so this number, this whole thing here in the parentheses, being ORed, bitwise OR with TCR1B register. Okay? OR it. And then you assign the result back to TCR1B. So all the zeros is doing the OR logic bitwise OR with all the other bits over here. It's not going to change anything because 0 OR anything is still that thing. It's not changing anything, right? So 0 OR A is still A. 0 OR B is still B. So all the zeros or all these things is not changing anything. But 1 or this single bit. So what is this bit here? Remember? CS10, CS11, CS12. That's the 3 bits in the TCCR1B, lower 3 bits in the TCR1B register. So I'm doing this OR logic. I'm not going to change anything for CS12 and CS11, but I'm only setting CS10. So after the result, after the OR logic, I'm putting, I'm setting this LSB here, which is CS10 to 1 as a result. So why this might be convenient in the future is that because now we understand what's really going on, okay? So in the future, if you want to set any bit in the register, you just use that register, do a bit OR logic, and put a 1 here and left shift by that bit. That's the goal, to make it simple. Any questions?
Yeah.
A lot of questions. Yeah, what's that?
Yeah, so you're saying that since we do the shift with the 1 by 0, that's setting the CS10 to 0?
To 1.
To 1, sorry, to 1.
Yes.
So it's setting the CS1 to 1.
Yes.
Then after we set it to 1, we're
Yes.
using the OR logic on the 1.
Yes.
Okay.
And we don't want to touch any other bits. Because this bit over here, CS10, is LSB of this register, right? So the goal is just to set that LSB to 1. And this is how we do it. So what about we are trying to set CS11 to 1? It's no brainer. We just replace CS10 with CS11. But we are not changing anything else. Just makes things easier. So when you are looking at the data sheet, right? So you look at the bits. Oh, I want to set this bit. Then just replace CS10 with that bit's name in this equation, and that one will be set instead of others. So this, by doing this, is actually not changing any other bits, but only setting that bit because we know the name of that bit, and we're gonna set that bit exactly in that register. Is that the only way to do that? Nope. Is this going to work? Yes. So the Arduinos they really like to be programmed in this way. Let's just keep doing this, keep it consistent. Is that okay? Any questions on this? Okay, cool. That's the first thing. So we are setting that to 1, which is gonna doing what? Let's look at that one. So what that does to us, right here. Here's CS10, right? I'm setting this bit to 1, so I'm having no prescaling. So by default, if I don't do this, by default, when you start up the microcontroller, if there's no previously loaded any code in there, so all the CS are zeros, all the registers are zeros. So just keep in mind, if you don't touch it, there should be zeros by default. All right. So if all of them are zeros, you can see no clock source. It's actually disabling that timer. The timer is not working. Okay. So by setting a prescaler, you are also turning on the timer. Keep in mind. It's gonna be on the quiz. By setting the prescaler, we are also turning on the timer. Okay. So if you want to turn off the timer, what you want to do? Give all zeros to the prescalers. Make sense? Okay, it's gonna be on the quiz, right? When I'm back from New York City, I'm gonna give you the quiz. I'll keep in mind.
Are you gonna get a chopped cheese while in New York?
Chopped cheese, what's that?
Chopped cheese?
I don't know what's that.
You gotta go to a bodega and get you a chopped cheese.
I don't know what's that, I'm sorry. Chopped cheese, I don't know.
So you said there'll be a quiz a week from today?
There's no quiz today.
Or a week from today?
It's a week from today, yes. Monday, yes. Oh no, Friday? No, Friday I won't be back.
Oh, next Monday.
Yeah.
Okay.
Yeah. Sometimes I just, tell you there's a quiz just to scare you guys, right? But actually sometimes there won't be a quiz. It just lets you pay attention. This is important. Okay, it's important. All right. So that's this guy, but understanding this guy, this will be easy. So what is this guy doing? Oh, sorry. What did I just turn on? This one. TOV. So TOV is the LSB of, what is TOV? Remember from the in-class exercise, the TOV is a timer overflow flag. It's just one single bit of the timer interrupt flag register 1, right? So the timer 1's interrupt flag register. So interrupt means whenever it overflows, it stops and doing something else, right? So that's another register, and this one will be automatically will be set to 1 whenever it reaches the maximum count of the timer. Okay, so by looking at this one, what's happening really here? Oh, this one. What is this happening? So similar concept. I'm moving that byte 1 to the left by TOV1. What is TOV1 being considered here? It's a 0. No, it's a 0 because that's 0, the bit 0. So it's being used as a number 0. You know what I mean? So you're actually shifting the byte 7 zeros and 1 to the left by how many bits? 0 bits. So it's not actually shifting that at all. So in that case, you are still getting a 7 zeros and 1 1, right, as LSB. That's the final result of this operation, and use that one to do a bitwise AND logic with this interrupt flag register. What is this gonna do though? What's happening? Why we are doing that? See this TF1RB, right? TIFR1. Sorry. TIFR1, this register has 8 bits, and the last one is TOV1, right? Okay. So if the counter is not overflowing yet, what is the value here should be? 0, right? When it overflows, it changes to 1, right? Automatically by itself. So in that case, if I have a 7 zeros and a 1 here, if I'm doing an AND logic, what's going to happen if it's not overflowing yet? What's going to happen? What's the result?
0.
Yeah, it becomes 0 because all these are zeros. It's doing AND logic. It's going to reset everything. And if this is 0 as well, it's going to be all zeros, right? All zeros. It's going to be all zeros. So if that result is still 0, that means what? It's still counting. Right? It is still counting. Working really hard, it's still counting. So in that case, while this is still counting, you have a semicolon here. Don't do anything. The timer is still counting, right? The timer is not up yet. It's still counting. Wait, okay? Semicolon will just wait there. You don't have anything, any curly bracket has any operations in there. Just wait. So whenever this is not satisfying anymore, because whenever the TOV1 here is getting flipped to 1 because of the timer's up, it's been 1, and you have this number doing AND logic, so this won't be 0 anymore, so this is not getting satisfied. It's going to jump out from this while loop and doing the follow things. That makes sense? So that's how you can generate a really accurate timing, because you're holding there until the timer's up. So when the timer's up, you'll do this. What is this? Stop the timer, because I'm doing all zeros, right? For the TCR1B. All zeros, which means all the prescaler bits are zeros. So I stop it. That makes sense, right? I start it while it's counting. Once it's finished counting, I stop it. Then you can start doing your stuff, right? So now I have timer stopped. Then I want to do this. What's happening? Remember last time in the in-class exercise, what I told you? Because this one has been set to 1 because the timer was up, right? So now I want to restart it at the next cycle. So I want to reset it, put it back to 0, so I can start a new cycle of timer again. So how to do that? Remember? I told you guys last. Give it 1 to set it to 0. That's the weirdest thing of the year. Remember? A lot of weird things in this class. The weirdest of the year. So you write a 1 to it. How to write a 1? Write a 1 to where? Write a 1 to TOV1, right? Write a 1 to TOV1. How do you write a 1 to TOV1? Still follow this format. So simple, right? Just follow it. Just plug in the TOV1 to it. That's the desired bit to be written to be 1. Then just put it into this equation. So we already understand it. We don't have to go through everything again, right? Just replace that thing to a TOV1 and also the register's name on the left side of the equation. That's it. And then you need a to rewrite that preset value of the counter so you can generate that desired period, right? So how to do that? Use the maximum counting, which is 2 to the 16th. This is the hex number. You have 16 zeros, trailing zeros. So this is actually 2 to the 16th, right? This is 2 to the 16th minus the desired count. So it's giving you a, remember this, the counting? TCNT1. So totally you have 0x 1 0 0 0 2 to the 16th. This is total count, and then you minus. So this is your desired count. Desired. Right. So use this guy, the maximum minus the desired. You are getting this starting value. So the starting value being stored in the counter register, counting register, and the counting register will start from here and then just finish the remaining counts, which will give you the desired frequency, which is what. So the desired duration here is what? Remember, after this counting, the following one is going to be directly flipping that speaker pin. So in that case, this desired count will give you what? See if anyone can answer that. Nope. But close. Remember what I'm doing here, remember? What I'm doing. I press it, so I have a while loop here whenever the price is being detected over here, right? Whenever it's being detected, when pressing, my finger is slow. I'm holding that on the button, and then I should hear that sound with a certain frequency because it has a certain pitch from that note. It's from the frequency, and when I'm holding it, it should keep oscillating. No, sorry. When I'm holding it, yeah, it should keep oscillating. Okay, so how's the oscillation frequencies being defined? Being defined by the timer. So now I got that defined, and then I flip that pin. that flip is just one little part of the oscillation. So what is that part? Remember? That's a half frequency of the oscillation, right? Here's the oscillation make the sum, right? Timer, flip. Timer is up, flip. Timer is up, flip. So you keep doing that to generate that oscillation. Make sense? And then you are done with that half period. Jump out from this, because this belongs to see here, right? Since you are still pressing on it, so it's gonna come back and keep doing it. All right. So you want to move. If you release it and it jumps out, and then will come back because this is a loop function. It will keep running it back and forth from the top, right? So what you want to do is after you release and press it one more time, it's going to detect this one. Oh no! Before it finishes the first one, right? So it get out from the while loop and get into here. So imagine that if we, for example, we started with I, which is the index of all the notes in this list over here, right? So these are all the different notes, give you different pitch, and so the I, when I was 0, it's playing this kind of counts, right? So once the first one is done, I was still 0, right? And I plus 1 is what? Is 1. 0 plus 1 is 1. And you do a division, integer division, but taking out the fractional part. That's what this operator means, right? It's just taking the remainder, fractional part of the division. If you don't know that, just search for that. It's very simple, okay? So 0 plus 1 is 1. 1 divided by 7, which is a constant we put in here, is 7, right? So 1 divided by 7 is what? As a fractional part of that division is what? 7. Its result is 0 and remainder is 7, right? No, sorry. 1. Result is 0, remainder is 1. Divided by 7. Right? Questions? 1 divided by 7. Result 0. Remainder 1. Okay. So 1 becomes 1. So next time you are moving to the second one, right? So and then keep going. It's 0, 1, 2, and keep going. You can explore all of them. And once this reaches 7, oh no, this is actually 6, right? So that you have 1, 2, 3, 4, 5, 6, 7. So 7 numbers in there, but this location's index is actually 6. It's starting with 0, so 0 to 6. And once it reaches 6, okay, so play the 6th position here. Eventually get out, and then 6 plus 1 becomes 7. So 7 divided by 7 give you 0. Okay, so you'll start over from the first one. Make sense? So that's why when you keep pressing, it's actually looping through and come back and doing that one more time. That's how that works. So that's the second one, which uses a timer, and the first one uses the microsecond delay function, which is the one you developed from tutorial 1. That's very simple, and it's just being controlled by the top button instead of the bottom one. So you can switch back and forth and try to play. So the number of knobs here is probably not accurate. So that is why. Is that accurate? So my question is, can you really tell the differences if I change the number of knobs over here? Because when playing using the top and bottom buttons, I couldn't tell from my ear, right? I couldn't tell. So in that case, it's probably kind of accurate. So if you start deleting 1, 2, 3, 4, and you could probably will hear a difference. Okay. If you want to try it, let me know. If you want to record it in the video, and that will be great. I really want to see how that works, how the differences are. Okay. So that's for this one. And any questions on the example code? So this is something that you can directly upload to your board and make it work. And the good news is everyone's board is working right now. That's great news. so I can sleep well the rest of the semester. Don't break it, okay? Protect it real well. I mean, someone is sort of printing a box, but you guys have boxes, right? Just the box of the blackboard, the original one. And just put it in there and take the black one out. Okay? Or just get any other box of lunch boxes if you want. Okay?
I don't have an analog sensor on my board.
What kind of analog sensor? What do you mean?
It's the one with by the IR, like the.
Yeah, there are a lot of all the parts are in the drawer.
No, it's got like analog SOT23.
Hmm.
There's none in there.
Did you see any parts are missing since you were there yesterday? No. No. Okay, just send me an email. I'll order more. Okay, so we don't have the IR until the 6th week probably. If you look at the schedule here, when back, we'll have PWM, RGB, and then the week after, right? It's gonna be October the 6th. We'll start doing the IR stuff, which is a lot of fun. I like that a lot. So we do the IR. There will be two tutorials on IR, 1 and 2 here, because the midterm exam, takes another week. So, and there will be a SD card, music playback, and DDS. The digital signal synthesis is actually generating analog functions. So that's very useful. So if you have used the function generators, right? So how these functions are being generated? Actually, these are digitally synthesized by different frequencies. It's a really fun project, and also the current quantum computers are actually using these digital synthesized signals as an input to do the measurement to the quantum computer, communicating with the qubits. So that's something that we have to know as well, have to learn. So definitely this whole semester we'll have a lot of fun. Okay, and eventually I think starting from like week 12, the 12th week, I'm gonna let you guys design your own board. So you have to learn how to use the Eagle PCB or Fusion 360 instead of just soldering, but also design the board and put all the sensors you have learned in the class, not everything, okay, just the necessary ones, and do the connections, learn the interface, and fabricate the board, solder it, and test it. That will be the final project. So it's going to be a full-fledged product. Okay. Any questions on that?
Project.
Hmm?
What's the group project?
What's the what?
There's a 10% group project grade.
No, it's not a group project. I don't think it's a group project. It's going to be individual projects. Yeah, I don't want you guys split the tasks, right? For example, you have a group. Then, you do the PCB, I'll just do the soldering, you do the writing, I do. No, everybody should learn PCB design and soldering. It's no choice. You just have to learn everything. Yeah, what's that?
Oh, I was wondering what we're building, like what we're.
Yeah, you have a lot of ideas.
We can do anything we want.
Yeah, towards the end of the semester, you propose projects, and so I did the same thing at Mines last year. So they proposed a lot of interesting things based on what they learned, like the IR stuff, IR sensors. They did a decoder. One of the students got really interested in the IR transmission. So it's like remote, right? Remote like these ones. It's the same frequency. So they were trying to catch any random IR signal in the air and then decode it. So they can hack into it. So they can easily duplicate this guy. Okay, so their microcontroller board eventually turns into a remote that they can hack into all these TVs and everything because they know how that works, right? That's one of the examples, and there were other examples by using the accelerometer. I think we leave some pins on the board for plugging in the accelerometer onto it. That will be another interesting project. LEDs, RGBs. I mean, you guys will have a lot of ideas, I believe, towards the end of the semester after you learn all these things. Also working with display modules as well. Display modules. What about do an eWatt? So you can sell it for $1,000, right? Just make that electrode array with. That's too much, a little bit too much. But that could be considered. Okay.
Are we all gonna come up with our own, or are we all gonna do the same thing? Like, are you?
No. You propose it. You propose it and prove it. I'll prove it. Right. I'll look into it and prove it. Yeah. The only ones I couldn't prove, like I'm gonna blink 100 LEDs and make it for the liquor store, like Bud Light or something. That's too simple, right? It has to be like display, digital communication, sensors, timers. So further, you'll learn interrupts and state machines, all these fundamental programming skills with embedded systems. Okay. Everything has to be involved. If you look at this one, this becomes different. Okay, this guy's different. See? I mean, let's just think about it based on what we just learned. Just think about it, how this works. I didn't press the button to play a note, right? So I press once, then it starts playing, explore all the notes in the on the list. And the song has a certain duration, okay? So it's not like playing dun dun dun, not that slow. And also it's not that fast, like dun 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 dun. It's not that fast, right? It's just a regular speed. If you want to make it into a regular speed, that so sounds normal, like a normal Twinkle Twinkle Little Star song. So you have to control the duration, not accurately, but normally. So you need a timer for the duration first, and during that duration, right, before you stop it and play a next note or do the break in the middle, because it's twinkle, right? So it's not like twinkle. So there's a break in the middle, okay? So that break has to be handled as well. All right, and also then when you get into during that duration, you are playing that note. It's a certain frequency, so you need another timer to do that, the oscillation. So you need the two timers, and the break can be a just simple microsecond delay. We don't want to involve like 3 timers. So it will be a nested timer controller. So 2 timers, one controls the duration. If you look at the code we just I just posted here. Oh, just keep in mind the task tools code is not provided. That's why I'm giving you guys entire week to work on it. Okay, have to work on it individually, never copy. Okay. So getting here, you can see what you guys can do. You know, for example, this guy, right? This guy. So definitely you are not doing this anymore because you are not really holding it to play it. You hold it once, then when you release it, it comes out. It gets out from the while loop. Then what you want to do? First, so let's say 2 timers. I already told you guys here, timer 1, timer 3, because these are the 2 16-bit timers. There are some examples over here, but you can see the duration between the notes is actually 1/32 of a second. So it's but if you do the conversion, it's about 30-something milliseconds. So that's between 2 notes, right? Twinkle. So that between these 2 notes is about 30-something milliseconds. And every note we play it for half second. Like twinkle, like this, right? Not twinkle, that will be 1 second. So it's 0.5 second, half second for the duration. And the frequency will be the frequency of that note. So that's already defined. You don't have to change it, and you shouldn't change it. So if we pick up timer 3 as 1-to-1 prescaler, so in that case, timer 3 is playing the note, playing the sound. Because 1-to-1 prescaler, we are not actually trying to slow it down, right? Because relatively higher frequency, we already did it in the example code. Right, it was a 1-to-1 prescaler and works fine. So it's a 16 megahertz, and we use a counter, we can do it pretty well. So for the timer controls the duration, I recommend that you use a 256 prescaler to slow it down because the duration is pretty long, like half second. So which one should be turned on first in the code, in the nested while loop? Which one should be turned on first? Timer 1, right? So timer 1 got turned on because timer 1 controls the duration. So timer 1 got turned on, So while timer 1 is on, right? While timer 1 is on, during duration, I get into the loop, I have another while, right? So I turn on timer 3, which is playing the note. So while timer 3 is on, I do all the oscillation. So once that is done, I get out from that one, and then I stop the duration. Then I play the break in between the notes. Any question on this? So the code is actually not very long. And the song, you can directly put all the notes in to a list like this. And you don't have to do this, but this is what I did. I'm picking up, so this is the whole song, the song I played in the video. And everyone has the E4, all these ones were defined by a number. It's actually taking out, so if you use this number and you can, so this number is this guy actually, 0, 1, 2, 3, it's actually this guy, I'm sorry, this guy. So these ones are being used as an index to take out a certain note from this scale. The scale is the list of notes, for example. Okay, that's by the definition. I googled it. So what is the difference between scale and notes? So a scale of a collection of notes. You may already know, but I didn't. So the scale of the collection of the notes. So the scale has all the notes here, right? And these are actually index. So whenever I'm playing one by one, and these are indexes. I put this index as an index of scale, so I can play a certain note from the scale. You know what I mean? So like E4 is actually playing this guy, and move to the next one. This one is still playing this one, and then keep going. So that's the whole song. But you don't have to do it. You can directly just put all the notes into a list and explore all the notes in there, which is fine. But this is just more intuitive. Okay, this is highly recommended. But finally, it's just very simple. You're just playing one by one, right? That's it. You have one index, which is fine. Just one index is getting, and then plus one, right? Just exploring all these notes. That's it. I think it's not a really complicated task given the time. You can work on it like for a whole week. It's due next Friday. Okay, so Monday there will be a new lecture on something else, but you do have a lot of time to work on it, right? Okay. See most of you on Monday.